Please, can you give me a feedback? Okay, great. Thank you so much. Okay, so we can go to discover. We can start to discover the motor catalog. That is one of the most important environments in FluxMotor. So let me take it. Okay, and let me take. Just for your information, today I shared some materials. The materials I shared today, the link is available in the chat. So if you are not able to find it, please don't hesitate to ask me. I can re-put it in chat. It contains just 3 chapters. I mean the agenda for sure, but then we these 3 chapters. We are in the general operation for the people that lose the first part of the training. And today we will start also the permanent magnet motor HEM design. For the general operation, we are seeing the environment, the supervisor, and all the aspects directly on the tool. But you can see also them in the second chapter here, general operation, that I shared, and you can go through the slides to check the functionalities. Okay, so just to clarify on also the content of the material I shared. Let me close it. Okay, the motor catalog is a dedicated application to allow an effective management of machines and project. So there are two main areas in the catalog. I'm talking about the motors area to visualize and manage all the motors stored, and the catalog area to manage directly the catalogs that we have here or that we want to have. For example, we can create a catalog, a new catalog to manage a single project in order to have all the motors that we are studying for the same project in the same place. Okay. Great. So the catalog is a folder. Each catalog is a folder that contains different motors of the same type, for sure. Each catalog need to have the same topology. And the folders that you can see, clicking on one of it, you can see the working directory here, for example, but also going into, also clicking on the other catalogs. Okay, and the folder includes an XML file. This XML file contains the main information about the catalog, so motor folder and attachment folder and so on. It's is a structure. So I don't want to show all of these things, but it's important that you just know where you can find your data on your laptop and so on. Okay, the catalogs can be shared. So you can share the motor, you can share a motor, but you can share also a catalog that is that contains multiple motors. So it can be, as I told, dedicated to a project. You can share it with the colleagues. You can share. You can load some catalog from your colleagues and so on. Talking about motors, we can, for example, going into synchronous machine 1, we have different catalogs defined depending on the topology, as I told. So we have the synchronous machine here and the induction machine here. In the synchronous machine, we have a permanent magnet inner rotor and outer rotor, mainly 3 phases for the moment, but the R&D team are working on the possibility to have n phases in your project. The reluctance synchronous machine catalog also is available, but let me take, for example, the permanent magnet inner rotor catalog, the predefined one, to show you the comparator. For example, okay, I want to compare the Nissan Leaf motor that is already available in the catalog, so you will find it on your laptop. The Prius 2004 and the Prius 2010. Okay, we need just to click add here to be able to have them in the comparator or compare, and then click on compare. So here we have the possibilities to compare the motors that we choose. Okay, in terms of dimension here, air gap, stator, operating condition, in performance, or machine characteristics, as well as masses and inertia. I mean, FluxMotor already know this data, because in this case, these motors are already let me say analyzed by FluxMotor. So each time that you do some computation, FluxMotor is able to store the parameters that you computed, and yeah, show you this parameter, and to show you these parameters in okay, in the motor catalog. So then you can just in the performance tab, you can just compare, okay, the constants, the power density of the machine here, as you can see. For sure, we can see a power density. The power density is increased along the years for the Prius, okay, and the constant of the machine and other parameters. Just clicking on cancel and the bin empty chart here to yeah, to delete them in the comparator. So the general data and the performances are available also without opening sorry, the model. As you can see, we have all the structural data here and the performance. For each motor, not for each motor, these data are available. As you can see, we have for the general data for sure, because in general, the model that you can find in the catalog is already predefined. But for the performances, not all the motors are computed. So yeah, some data can miss. You can just edit one of these model if you are interested in it, and start the design, or directly start the computation and then store the results. Okay, great. So I think we we end the general operation chapters, and we can start with the permanent magnet motor electromagnetic design. Okay, so let me take the this chapter, and now along this chapter we will see an overview. I mean, how to start with a new project, how to design a new model, new motor. Yeah, thank you. I can put again the link here, no problem. Let me just take it. Okay. We will see how to design step by step the model, and we will see some characterization tests such as Cognitorque, PKMF, model datasheet, and the working points test, scene wave mainly. to hand with the performance mapping test and the duty cycle. So, okay, just a brief overview before start the exercise on the, let me, okay, just a brief overview. Okay, before start the exercise, we will see mainly today the electromagnetic test. For sure, we are not able to finish the exercise today, so we will end it tomorrow at the beginning of the second session. The electromagnetic test that we will see includes 3 different categories. The characterization tests that are open circuit, model datasheet. The thermal will be considered in also tomorrow, but in a separate, it's in another chapter. The working points, we will see the sine wave one, the performance mapping with the sine wave sources. And in the performance mapping, we will see also the duty cycle. We will consider also the duty cycle. Yeah, I don't want I will spoke about each test during the exercise, so we can just check the model that we are building, that we are going to building. The problem description is an EPM, as you can see, an EPM motor, so interior permanent magnet motor. The power is 80 kilowatts, and it's very similar to Nissan Leaf motor that we have in the catalog and in the real world. So you can see here some pictures of the motor. Such as the dimension that contains dimension for sure, internal and external. So the main dimension here, some picture of the water jacket, a picture of the single sheets of the rotor that will contain then the magnets, here the cooling and so on. We have the motor with the end winding visible. Here we have the connection and the housing, just a brief description of the housing, as well as the motor dimension and the winding design, the configuration. So we have 48 slots, 8 pole with 3 phase. As outer diameter of the stator, we have almost 200 millimeters. And the rotor mass is, for example, 16.45 kilograms with magnets, and the magnets is less, the mass of the magnets is less than 2 kilograms. So just a picture of the motor built in FluxMotor. Sorry. Let me take a look at the chat if some question is there. Okay. So the configuration is already declared, as you can see here. This is the rated power at 4,000 RPM. We have 375 DC bus voltage and a maximum speed of 15,000 RPM. Outer diameter, stacked length, and the air gap. Air gap is 1 millimeter. The lamination material is M313-35A. It's a material that is already available in our catalog, as well as the material for the magnet, that is a neodymium one. We have a 3-phase single layer winding with a coil pitch of 5. We will see how to design and define the winding for sure today. The number of coil per pole per phase is 1, and the number of turns per coil is 6 with 2 parallel paths. We also have the flow for the water jacket cooling system, but this is not used today for sure, because we are going to define just to compute the electromagnetic performances. Okay, so we can start. Let me take, sorry, let me start from the motor catalog. Okay, and you have to click on catalog, because this time we want to create a new catalog dedicated to our project, for example. Okay, and so you have to click on catalog and then click on this icon, create a new catalog, because we want to show you how to do it before start with the design. Okay, and so when you click on create new catalog, a new windows appears. We need to define some data to create the new catalog, starting from the name. That could be FluxMotor Training 1, for example, just because I already have this catalog, so I can't create a new catalog with the same name. We need to define the family of the motor, so synchronous or induction. In our case, it's an EPM motor, it's a synchronous motor, so synchronous is fine. The type is permanent magnet with inner rotor and 3-phase. It's fine. Again, you can choose the working folder or just keep the suggested path from FluxMotor that is the same that you already defined or you automatically have as a set in from the supervisor. And by the way, we also have here the author that by default is the name of the laptop that you are using. Okay, in my case is Ferrara. Just clicking here, you can also put a comment, but is not, I mean, you can also leave the field blank. And you can click here to be able to see the new catalog. Okay. So once we have the new catalog, we can click on motors here. Okay, and click on this time just selecting the catalog that we are interested in. Click on new. In this case, we are starting from a blank, I mean, but we can also, for example, choose this motor, for example, and create duplicate. But since we want to start from we don't want to start from a specific case. I can show you, I will show you how to create a similar motor just starting from a blank. Okay, so when I click on new here, a new window appears. It's creating the name, is creating a motor, and we need to put a name for the motor that we are going to define and to test. So the name could be EPM 80 kilowatts EM. In my case, I put day 1, but it's the same. I mean, okay, and the motor factory appears. So the motor factory is the only part of FluxMotor that we didn't see before. And is the main important section of FluxMotor because here we can do the design, the test of our motor, and we have the access to all the export function. Okay, so normally the workflow is from the left to the right to complete all our tasks. Also in the test here, normally we start with an open circuit test, and we complete the computation of our machine with the performance mapping. And in general, we need to start from the design. So we need to design the motor, to test it, and at the end, we can export the model if we are interested in it. Okay, so okay, just to start with the design, we need to start from the topology here, and click on the topology icon on the top ribbon. We need to select the dimension input mode here, and the right one is the stator for our exercise. Is the stator inner diameter is the resulting dimension. This means that sorry. This means that we can define the outer diameter for the rotor, the air gap, and the outer diameter for the stator. So this diameter, the internal one for the stator, is computed depending on the data that we will enter. Okay, in fact, you can see that clicking on this function, this appears in light gray, so it's not changeable. Okay. Great. So we need to put the right dimension. So we need to enter the main dimension and the number of slot and poles for the machine. Starting with the rotor, we have 130 for the outer diameter. The inner diameter is 44.5. The length is 150. And the number of poles is 8. So the length of the air gap is 1. The number of slots is already set to on 48. The length of the stator is the same of the rotor in this case, so 150, and the outer diameter is 198. Okay, so once you enter all these data, you have to apply inputs, and a new alert appears, as well as the red color for the design tab and the red color for the winding here. This means that the slot filling, if you move your cursor on it here, you can see that the warning is edit motor winding. The slot filling is not valid. This means that with this winding, with the winding defined like this, the turns, I mean, we are not able to reproduce it because we don't have enough space. And this is due to the fact that I mean, we had a bigger motor just before, so it's not a problem. It's something that we will fix along the design process when we start to define our winding. Okay. So we can continue. About the housing and the shaft in the machine section, we don't need to define them since we need to perform just the electromagnetic analysis, and so it's not. Oh, sorry. So it's not what we need to do now. Okay. We can go to the rotor directly and choose the magnet, so the rotor part. In this case, we need to change the shape and the topology. So we can click on magnet shape to change the parts that we want to consider in our model. In our case, when you click on magnet shape, the library for the internal parts are available. And we need to change a part from the IMI layer library. So from this one, the part that we want to consider today for this design is the IMI layer 10A. So IMI layer, we have to scroll it down. Is this one? Great. IMI layer 10A. Clicking on OK, so apply inputs. Again, don't worry about the warning, we will fix them later. The new part appears on our view with the inputs that we have and the outputs parameter we have. So what we need to do now is to enter the dimension of the magnets and the parts and validate the inputs. So let's start with TM1. Just a comment, tip. If you move your cursor on the on the name of the single input, you will see a description, a brief description of it. So in this case is outer magnet thickness, okay, and you can see also from the view what is referring to this parameter. And then click on the number. You can you are able to just modify it. Okay, so we have TM1 3.862. Okay, we have for the width of the magnet 28. We have H1, so is this distance. We have 2.5. We have done W1 is 1.843. For V1 is 15. TM2 is 2.6. WM2 is 15 again. H2 is bigger, so it's 21. Then we have W2 is 1.843. T2 is 10 because we want to move these magnets in the internal parts of the rotor. The V2 is 124, and the last parameter is 0.5. Okay, so clicking on apply inputs, we can see that the geometry is changed, and we have thickness. We have a quite great thickness of the external magnet, and we have other two magnets here that are quite distant from the first one. So the part is definitely changed. Okay, so in this case, there is no skew on the rotor for this motor. So if needed, a continuous skew can be defined through the skew tab. This is the continuous skew. And the skew angle can be defined either by slot pole pitch radio or as shift angle. It depends on your needs. Okay, so now to handle the rotor design, we need to check the polarization. And so here we have the polarization. You can see in the view that is correct, is already correct. We have 1, 2, 3, 4, 5, 6, 7, 8 poles. Okay. We can go to the stator and choose a different slot shape. In our case, clicking on slot shape, we can choose another part for sure. In this case, our part is in this library, or has PL truth, and the part is the 01 F. So is this one. Okay, clicking on apply on choose this part, we will see that the geometry is changed. And now, as before, we need to enter the inputs parameter to be able to have what we want to have here. So let's enter the dimension of the slot and validate all the parameters. So HS is 21.1. WT is 4.2, is the length of the tooth, the width, sorry, of the tooth. HO is 1.2. Then we have the slot opening, that is 2.8. V, that is this angle, is 27. And two hand with the fillet radius that is that can be left as the default one. Don't worry, as I told, we are able to fix all the warnings on all the problem with the winding definition. Okay, so we have now a new geometry because we changed the parameters with this of this new part. Okay, and okay, in the lamination, we also have the lamination tab here that allow the definition of the outer shape of the lamination. So can be circular, can be rectangular. No need in this case to change it. By default, the outer shape of the lamination is circular in any case, without extension, by considering the outer diameter of the stator, so that we define the structural data. Also here, this queue can be defined as before, a continuous queue. You can just click on it and enter the parameters that you want to change. We can proceed with the winding now. As you can see, we have a classical and hairpin winding. Hairpin is also are also available. Under winding, we need to select the star connection and select the definition mode as auto, that is that are by default, and enter the number of parallel paths as 2 here. Clockwise is fine. We need just to click on apply inputs. Okay, and the winding icon is shown in red due to the warning, as I told about the slot size, which isn't consistent with the coil definition. So let's fix this problem. Okay, as you can see, the problem is here because the wires are not have not enough space in the slot. So let me correct it, and then I will. Okay, let me just better explain the definition mode here. So there are 4 different modes to define and build the winding architecture, with each mode allowing more inputs and more control by the user for sure. So we have the auto one that we are using, but there is also the easy one. As you can see, some more parameters are available to define our winding. The advanced one to end with the expert one, where we can define the connection table, so called coil per coil, enter slot and outer slot to define each coil in our model. In our case, we can keep the auto, just the feasibility of the winding configuration is ensured just for auto and easy model. So if you decided to use the advanced mode or the expert mode, the feasibility of your winding your responsibility. This is what I am trying to say. Okay. Instead, if you use auto or easy, it's I mean, it's insured. Okay. We can now we can fix the problem here, going in the coil section. So under coil, make sure that wire topology has circular connection. Okay, here, circular one. The slot filling is orthocyclic, and the grouping method is grouped. Okay, then we have 6 turns per coil. The number of wires in end is 20. But we need for sure to change the wire diameter to be able to have all these wires and turns in the coil and in the slot. So here we can click on wire diameter without insulation, but in our case, let me just. In this case, we need to have the AWG, that is the wire diameter with insulation. So our wire diameter is the 20 class, is the class 20, that has 0.813 millimeters. Okay, the interwire space, sorry, can be leave as by default, and the twist is not necessary in our case. We can just apply inputs and see that now the wires are colored as different colors depending on the number of turns that we put. Okay, and yeah, they are in our slot. So the red color for the winding disappeared. Okay, great. Then for insulation here and winding, X factor, the default values will be used. Just I mean, just to it's important that you know that in the insulation tab you can define the liner, the impregnation, and so on. Some parameters that we will see tomorrow when we will need to define our machine also for the thermal study. And about the end winding also, it's quite powerful to define. It's quite useful, sorry, to define them for the thermal study, because the end winding geometries can help us to achieve accurate results in the thermal analysis. But for the moment, we can leave these 3 tabs as default. The X factor contains just some factor that we can consider along our design process. So the cooling section is in light gray, because without housing and shaft we can't define the cooling system. We will do it tomorrow. The last part of the design process is the materials. So is define the materials for the machine. We have here. Let me just control if we have some. Okay, can you repeat magnet selection? I lose the message, so I'm so sorry. I'm going to end the design section, the design workflow, and then I will come back to the magnet one. Okay, so here we have the materials for the materials that we need to use in our machine, starting from the rotor, going to the stator, and also for the cooling. In this case, we already have some predefined material, but we need to change, for example, the material. Just a moment. Okay, we need to change the material for the magnets. We need to have a neodymium magnet. So the ref is this one, 1,230, 1,400. Okay, the magnet circuit instead is the same that we have here. The coil conductor are made by copper, and we also have Nomex as insulator. Also, the thermal fluid can be lived as this one. Okay. We need to click on OK to make efficient the modification, and I can come back to the magnet design. So to the rotor design. To choose the magnet, you have to click on the magnet shape here, okay? And our part, if I, okay, is IMI layer 10A. This means that you will find it in the library IMI layer, that is this one, and then you can just put the cursor here where you have the parts, okay, and scroll down until you find your part. So, for example, IMI layer 10A. You can just click on it and click on choose selected part. And then you have to modify each input parameters here and click on apply inputs. I hope this replied to your question. Okay. Another important thing that I didn't mention, so it's in fact the winding design phase. Okay, so just a moment. Also, you define the winding. You have then the view. You have some pictures and some data available of your winding. Because it's not an output, but I mean, it is an output depending on the data that you put in the winding section. So we have the possibility to have some characteristics here about your winding. You can see the number, the coil layout, the pole distribution, the pole pitch, and so on. But mainly what I prefer to have, as well as the resistance for each phase, the inductance. We can consider the end winding inductance, the end winding resistance, and the end winding inductance here. Clicking on inductance. Okay, this value is quite useful when you need to perform some analysis with the finite element model. Sorry, like flux, because normally this value has to be computed manually by the user. So it's something that you have to add in the circuit, but it's not a no value, a very no value. You have to consider to compute it considering the end winding geometries. So in this case, you can just define the end winding here in the winding section, and then take this value to consider. We have also some data on the masses, on the costs, okay, and especially quite useful for sharing the data with the people that are in charge of the building of the motor. You can share the layout, the connection table that is automatically built depending on the data you put here, the radial view, and the axial view. I mean, the axial view is not so useful for for this purpose, but we also have the MMF analysis, so the spatial analysis, the spatial representation for the magnetomotive force. On the versus the mechanical angle, we have the harmonics for our winding, and also the harmonics in table. To go through the winding factors, in two different representation, so tables and graph. Two hand with the slot star that is able to show us if the system is balanced. Okay. So, okay, please check at least the slot star before going into the test section. Okay. Okay, so we designed our motor, and now we can start to perform some analysis on it. So when you click on test, you will have the radial view here and the test overview here. Okay, you can just save the motor changes, because tomorrow, so we are not able to hand the exercise today because we don't have enough time. So please save the model now and at the end of the section, because tomorrow we will start from this model. Okay, so please, this is the button to save, to be able to save your model and the modification that you did in your model. Okay, so once you click on test, you will have the test overview here at the left of the screen that summarize all the tests that we already did on our motor. For the moment, is empty. For sure. We just designed our motor, and we don't have some tests already done. And please remember that each time that you go to the design process, so to the design stage, to change some parameter, all the tests that you did will be deleted. So if you want to change something, please store the modification, or you can use also the store motor button. So this allows you to store different motors in the same catalog in order sorry, I'm very sorry, in order to have the different motor dedicated to the same project. So if I decide to, for example, improve and change the height of the magnet here, for example, and I want to analyze the motor with this change, I can just click on the store, do the modification, click on the store motor, and then perform the analysis that I want to do, to be able to compare then, using also the comparator, if you want, the performance of this new motor with the previous one. So it's quite powerful to manage the models or the single project. Okay, so, but now we want to start with the test. So we will start with the characterization test in open circuit for sure. So let me take let me click on open circuit, and here we will see that we have a Cogn torque test and a BKMF test available. This means that we have these two tests are already set and ready to be performed. Starting with the Cogn torque, I mean the purpose of this test, starting with the Cogn torque, we want to obtain the Cogn torque of the machine and evaluate the impact of the machine topologies. I mean, the Cogn torque is normally depending just on the configuration, so on the magnets and the number of slots that you use, the number of poles, the type of the magnets, and the Cogn torque is useful to check the resistance of the motor to the rotation. Okay, so for this test we don't need input because yeah, we need just the geometry of the motor, but we can consider for sure different temperature for the magnets. These characteristics, this data is important because the temperature change the properties, so the power of the magnets, as you know. And so this can affect the results and change the results also of this test. So not so much for sure, but we can consider, for example, another temperature. I mean, it's not so interesting to check the thermal dependency in the cog-in-torque analysis than probably in the BACMF one. As input, non-input, no input needed. But if you click on the here on the previous icon, we can see that we have some inputs that are set by default by FluxMotor. So you don't need to change anything. You can do it if you want, but yeah, no input needed. Which are the inputs for, in this case? So for this analysis, we have the number of computation in the cog-in-torque period. Since we have, I mean, a period, we need to have at least 40, 50 points in the period to be able to discretize, to well discretize the period. And in fact, by default, is 45. We can change the number of maximum harmonic to consider. We have also the rotor initial position that is not so useful for this case, but you can change it. And the air gap mesh coefficients. So the air gap mesh coefficients is a coefficient that allows you to consider a different mesh. So you can just modify it, but by default, I suggest you to keep the default things. So, okay, we can just click on start to start the test. Okay, about the air gap mesh coefficients, if you put 0.1, for example, you will have a more an higher density in the of the mesh in the air gap. So if you use a bigger value like 1, for example, you will have less elements. About the cog-in-torque period instead, so it can be computed considering the formula 360 degrees divided by the least common multiple between the number of slots and number of poles, that in our case is 360 divided by 48. And so we will expect 7.5 degrees for the period as period of our cog-in-torque. Let's see. Yeah, this is confirmed here. Great. So each time that we finish some test, you will find in the section here the results. So we have the inputs here, the settings and the definition of the magnets. But we want to check the cog-in-torque because this is the exercise. So we have 7.5. We can check the magnitude peak to peak from the table, but also from the graph here. We have a quite good, a very good shape of the cog-in-torque here and we have just one period with 45, I remember you, 45 points, solution points. We can check also the magnetic circuit loads, so the magnetic induction in each part of the machine. And we can check the cog-in-torque harmonic analysis. We can check the harmonics content, the harmonic content of our cog-in-torque. We have just the first and the second harmonic, and the bit for the fourth one and the sixth one. And the same values are available also in the table. Okay, so we can continue with the BACMF analysis. Okay, the purpose of this test is to characterize the behavior of the machine when running in open circuit state, for sure. The analysis is the first step to evaluate the relevance of the machine normally, design regarding parameters such as topology, winding architecture, composition of coil, and choice of the material. So just one input is needed in this case, that is the speed that we want to consider. Let me check if we have some question. Okay, no. Don't hesitate to write your question in case in the chat. So we have the speed here as input, as only input, and the speed that we want to consider is 4,000. Okay, we have to click on apply inputs, but we want also to consider a different temperature for the magnets, because the back-MF test can be done along a test section on your bench, and so the temperature on your machine can be different. So just to show you that we can do it, we can click on thermal here and put 100 degrees for the magnet temperature. Okay, so the speed is 4,000. We can just click on apply inputs again and start the test. In the meantime, I will show you the other parameters that we have. For example, as before, the number of computation in the electric period before was in the electric, sorry, in the Coggin period. Now we need to consider the electric period. The maximum harmonic order, that is the same of the previous example of the previous test. We also have the rotor initial position that is normally set by default on auto, and the mesh order and the air gap mesh coefficients. So these two parameters are referring to the mesh that the model, the embed finite element model has. And this means that by default we have a second order mesh, of the model. So that means that the model is quite accurate, you know, and the air gap mesh coefficient is 1.5. So as you can see, the time to solve the model is very fast. Also, if we have a finite element model in the ground, because FluxMotor is able to set the mesh in a proper way, so to carry out a quite accurate analysis without take a lot of time. Okay, so you can change in any case these parameters if you want. You can also click on the here on help on the question mark here or here, depending on your needs. But in this case, to have the access to the user guide and to check all the details for these two tests, as well as the limitation we have for these parameters and so on. Okay, so now the test is finished. So if you click on test here, we can see that we performed the Coggin torque test and the back-MF test. Okay, here the test has been solved. Great. So if you re-click on back-MF, you will find the results. We can save the motor changes. Please remember to do it, because tomorrow we will restart from here. And we can check the open circuit in the main results here to the clicking on the main results open circuit. We can check, for example, the results as the voltage constant here. We have the back-MF characteristics, the flux linkage, the flux in the air gap, the flux density in iron, and the magnet behavior. Then we can scroll down here and check all the graphs and tables available, such as the phase voltage in open circuit. We have the graph here and the harmonic content, the harmonic analysis. The same results in the table as before. And then we have the line voltage versus time, the harmonic analysis on the line voltage, and the same results in table. To go through the magnetic induction in the air gap, we can see here the shape of the magnetic induction in the middle of the air gap. Again, the harmonic analysis on this curve in table and in graph, and the flux linkage here versus rotor angular position in open circuit. Okay, so this is the flux that invests the coils, the winding. To conclude with the ISO values of the machine, where we can find if we have some parts if we have saturation in some parts, also in back-and-forth analysis. This can be see because we have a very thin web, and so some parts of the machine is quite expected that can be saturation like this. But the most important values are in the teeth here, and we can check the vector potential also to check the flux lines, and we can also check the mesh, okay, that FluxMotor uses to carry out the analysis. So please remember to store the motor changes. Tomorrow we will start with this exercise with the characterization test model. I hope that this session it was useful for you, and if you have some question, don't hesitate to contact me to open a new question on the forum or on the support section, please. So thank you so much, and see you tomorrow. Have a good rest of the day. Bye-bye.